This is the second in a series of videos in which I'm attempting to repair this Wren executive computer system. This is the third of these machines that I've repaired over the last few months, and if you've been following these videos then you'll know that there's been a whole variety of faults, failed ICs, poor tracks, battery leakage, failed floppy disks, this sort of thing. And I've been working my way through the machines, and all through the repairs, one thing that's been a constant source of aggravation with these machines is the reset circuits. And this is quite an advanced machine. There are quite a few nice features that it's got in terms of bank switching. The in-out circuits are quite nice. It's got a built-in modem, a USART built-on video display controller. It's got a mixture of DRAM and SRAM, a keyboard controller, separate video RAM, and it's got some other in-out interfaces, a sound chip, and overall it's a nice design in terms of the features it's got, and it's been fairly thoroughly thought out in terms of the features they wanted to build into it. Unfortunately, some of the simpler parts of the system, in terms of the basic design of a system like this, don't seem to have been thought through quite as well as I think they could have been. Now, in particular, the reset of this machine is somewhat untidy. All the different parts of it come up in a slightly different way. So what I mean by that is when you first power this on, the various circuits are reset in various ways. But because of the way that the reset circuit, the basic reset circuit on this is arranged, it can cause an issue when the system is booted up. And the system also differentiates between a cold boot and a soft reset. So when you first power this up, there's a resistor capacitor network that is used to time the initial reset pulse, and the reset button doesn't do anything other than discharge the capacitor that's in that circuit. So in theory it restarts, but the system differentiates between those two because certain registers are set or certain latches are set in other parts of the system. So it kind of knows that it's already booted. The problem with this is if the circuits that are meant to control things like bank switching don't reset properly when power's first applied, then when the system tries to boot by reading data from the ROMs, it ends up reading data from the wrong bank. And that's true of the other devices as well. If the reset isn't successful, then they come up in the wrong mode and the system will in general crash. And that's what tends to happen. I was finding that on the different machines it varied in terms of how many attempts it took to get the machines to boot, and it was largely dependent on the condition of the various ICs. I've mentioned in the past that ICs tend not to always just fail, sometimes their performance degrades, and with a circuit like this with so many different interacting parts, you could spend a lot of time going through this and replacing parts because the boot up is a bit erratic. And this particular machine was probably the worst of the three that I've done, in that it almost never booted up successfully the first time. You had to press the reset button, and I went through this in quite a lot of detail. I'm waiting for some parts to turn up so I can complete the repairs. And while I was waiting, I thought I'd go through and look at this reset problem, see if there's anything I could do about it. Found various issues with this particular board. There was a buffer down here that was causing an issue, and when I replaced that, it would boot probably 50% of the time, but even so it wasn't 100% successful, and as often as not it wouldn't boot up, and the general symptom was either the caps lock light would come on and stay on and nothing else would happen, or it would go directly into the common RAM test mode and that would fail. But when I put a logic analyzer on, there was no reason for this to fail. It was seen to be doing the right thing, except it wasn't fetching the right instructions. Now when I put a current meter on the supply, what I noticed was that in the instances when it failed to boot up properly, most of the time it was drawing excess current, so it tended to indicate that the hardware had not initialized properly and there was more than one device trying to talk onto the data bus at the same time. And that's probably also why there are so many buffers failed on these machines. On all three machines there were a lot of 74LS 244s and 245s that had failed, and they were mostly the ones that put data onto the data bus. And if it's booting up and allowing them to come on in such a way that they are there's more than one active at any one time, then that explains why there were so many failures. It also explains why the DRAMs seem to suffer so much, because they're kind of in a direct firing line as well when that happens. So trying to track down what was causing that, looking at it with the logic analyzer and looking at the various timing for the reset pulse goes to a lot of different areas on this board, and looking at each of the circuits in turn that require the reset, it became clear what was going on. The time constant for the reset circuit was set something around the 1 second mark, and the way the resets arranged on this is very simple. There's a resistor connected from the 5-volt rail, goes through, and that's over here, goes through to a capacitor, which is over here. That's connected to the input of one of the LS244 gates, and that's a SMIT gate. And then the output of that is the reset line that goes through to all the various circuits. The problem with that arrangement is if you monitor that when you power up, because the SMIT gate only works when the chip's powered up properly, then as the chip is powering up, that SMIT mechanism doesn't work. You just get noise on the reset line, and that was causing the processor to start and stop. This is all happening very quickly within a few milliseconds, but the Z80 itself needs a few clock cycles with the reset line stable low to do a proper reset. It was starting up, various circuits weren't being reset properly because of the multi spike on the reset line as the power came up, and some of the circuits were coming up randomly depending on exactly how the power came up and what the state was when the power went off. Also, to get it to reset, you had to either power it off for quite a long time or power it off, hold the reset button for a few seconds, which discharges the capacitor, and then repower it, and it would usually then come up 50% of the time again. So it wasn't very convenient, and I wasn't particularly happy with that, but I don't think any amount of chip swapping would have made much difference. So I decided to take a slightly different approach and try and find what I hope is a bit of a more robust solution. So looking at the time constant required for all the various circuits, it looks like the time constant needed to be about twice as long for the reset pulse at power up. So that's what I've done. I've changed the resistor value. It was 47k, I've gone up to 100k, retained the same capacitor value, and I've put a reverse bias diode across the resistor, so when the power goes off it will discharge the capacitor far more quickly. And so what I've found now, after having done that, I've run this through boot up about 100 times. I'll just boot it up again. And as you can see, it's booted up fine. I power it off, we'll give it 2 seconds, power it back on. Now previously if I'd done that, it would have just crashed. It wouldn't reboot like this, and it needed quite a long time between power off to power on before it would reboot. I've been through this many times now, and it does seem to be pretty much 100% reliable in terms of its boot up, having changed this boot up reset time constant. Very simple change. It's just changing a resistor value, adding a diode, and it's made a world of difference to the machine. It now, as I said, it's booted up properly every time since I've done that, and that's probably over 100 boot ups while I've been testing other things, and I haven't had a single instance where it's failed to boot up. And again, through reset, using the reset button, it comes back fine every time now. Okay, so if you do have a Wren and you're getting boot up problems, that might be one solution. It's R11 in the corner next to the reset button that needs to be changed. As I say, it was 47k. I put a 100k resistor in and put a diode across it backwards so that it gives you a faster discharge time when you turn the power off. Okay, so that's where I am with this board. I'm waiting for a new floppy drive controller to turn up. One of the floppy drives is faulty, so I'll be posting a separate repair video for that, and hopefully at some point we can get this machine to boot to the operating system from floppy disk. Comments welcome. If you do have a Wren and you've got any interesting stories about it, then please leave a comment.